The origin of Google DeepMind lies in playing games. They trained AlphaGo to play Go, and which then beats Lee Sedong in 2016. They used this research to build Alpha Tensor, which found a new way for matrix multiplication. And this is now used in Google data centers to be 1% more efficient, which saves billions of dollars every year. So playing games or solving games with reinforcement learning leads to real world advancements. Also playing games is great because you have verifiable rewards and you have infinite data through self-play. We want to look at Snake, where the snake grows every time it eats. But why would we be interested in a 50-year-old game? Well, we want to look at n-dimensional Snake. So we can increase the dimensions where the snake moves in the third dimensions by jumping here between the 5x5 planes. It's a cube. And here we have 4 dimensions. Here we can represent this by moving in the y direction between the 5x5 grids. 5D, we move between the 25x25 grids, and so on for 6D and 7D. Yes. Why is it interesting looking at higher dimensions? Well, robots, for example, they have 7 dimensions. They have the dimensionality of 7 for movement. And also, you never know where this research leads, as with the example with Alpha Tensor. So what are we looking at? So we want to know, how does dimensionality scale? Does the performance of the agent degrade at higher dimensions? And also, how much more compute does it cost to train at higher dimensions? Is there a dimensionality at that training breaks down or learning breaks down? And what is the best state representation? State representation is how the agent observes the world around itself. We could do this like humans. For example, like use a CNN to observe the whole board. But there's a problem that the features grow exponentially and also the board, so it would take way too much compute. Also, in PyTorch, we only have 2D or 3D kernels, so implementation would be very difficult. We need other state representations. One possibility would be the local grid, where we have an n-dimensional hypercube around the head, where we observe the world and we also give it the direction of the food. But this is also exponential feature growth. So we came up with the array-based approach, where we look in all directions and give it the distance, and also tell it if there's the food or in which direction is the food. And this way, we hope to scale better at higher dimensions. We give it 100 reward if it plays perfectly, if it fills the whole board with its body, 10 if it eats food, -10 if it dies, and otherwise takes 0.01 away. We use double DQN to train the agent, as it is stable enough, and therefore we do not need PPO. When we look at board utilization, that is how much of the board we fill with our body. We perform really well at low dimensions. This is state of the art, but that drops off at higher dimensions. But here we could also wonder, because episodes take longer to train at higher dimensions, what happens if we give it all the same amount of episodes to train? And here the drop is not as stark, but still it is there. Although we see even a slight increase from 2 to 3D in the local grid state representation when we have a wall around the area. And the time to converge is exponential, especially for the local grid-based. And here it takes way longer to train compared to the array-based state representation. Why is the training time lower at 7 or 8 dimensions? This is because learning breaks down, so it doesn't learn anything, and therefore it stops faster. All in all, we had success in training and reinforcement learning agent at higher dimensions. It could even, like, that just achieved 5% at 6 dimensions doesn't mean it didn't learn. The body still grew to a few thousand in length, just the space is really, really big. And then learning breaks down at dimension 7. Here we might need another architecture or a different state representation. We had only marginal performance gain from local grid state representation to over array-based state representation, and therefore this doesn't justify the exponential compute growth and cost. And here we clearly recommend the array-based state representation. Thank you very much for reviewing us, and we hope you enjoyed HyperSnake.